Okay, here's some graphics that may help us understand a little bit. Now, in the case of a line, we have a constant slope, unlike other curves. The equation of a line is y equals mx plus b. And I don't know what this is. That's not correct. There we go. The equation of a line is y equals mx plus b. And no matter where we look along the line, if we take the change in y over the change in x, we're going to have the slope of the line. And no matter where we measure that, no matter how we change x, the change in y is always going to be correspondingly the same. And so we have a situation where when we take a look at the change in y over the change in x, which is y2 minus y1 over x2 over x1, well, in this case, here are the coordinates. This is y2 up here, and this is y1. And we have x2 up here, and x1 down there. And that's going to give us the slope. Well, y2 is given by this expression, y equals mx plus b. And when you take y2, which would be this expression here, m times x plus delta x minus y1, which is x, y equals mx. I just factored out the m, divided by the change in x, which would be x plus delta x minus x. These two cancel out. They're just one, and it leaves the constant m. So delta y over delta x is m. And when you take the limit of a constant, and here we got an arrow there somewhere. Yeah, there it is. As delta x, the limit of delta y over delta x as delta x goes to 0 never changes. It's always the same. It's m. And so the tangent is the same all along the line. We don't have any change, so it's a constant in the case of a line. Here, in this other situation, we have a curve that changes. Where you move along the x-axis, we have varying values of x. We don't have, like a line, we don't have a constant result. So if, in a line, we have predictable, we have a curve that doesn't change in the sense that the rate of change along the curve is the same no matter where you are along that line. The rate delta y divided by delta x is always going to be the same. Here, this isn't the case because we have the situation where when you move along the x-axis, the y value is the square of the value of the x-axis. So we have quite a significant change in the values that y take on when you move along the x-axis. And as you can see here, when we apply delta y over delta x in an arbitrary way around, let's say, at a point P that we're interested in. And here at the point P, we have the tangent line. This is the real tangent line at point P. You can see that how we choose our rectangle or triangle, our right triangle, we have an approximate slope on the hypotenuse that gives some kind of an approximation of the tangent line at point P. Now, in this case, it's not a very close approximate. You could see that it made a secant here. It cuts off the curve, divides the curve of the function. So it's an approximate estimate of the tangent line. But what we do see is if we shrink our base, our delta x, our corresponding delta y also moves down, but that the slope of the hypotenuse of the decreasing triangle, okay, the triangle gets smaller and smaller, the slope of the hypotenuse changes, and it begins to more closely approximate the tangent line at the point that we're interested in, at point P. And as you can see here, with a small triangle, the hypotenuse line is closer in slope. It's becoming more parallel than the original hypotenuse that we started out with. So what we're interested in is coming up with an expression for our change in y over the change in x, and then taking the limit and squeezing delta x to 0, because when we approach 0, the hypotenuse of the triangle becomes increasingly closer to the actual tangent line at the point P. And in the limit, it actually becomes the tangent line. So we're interested in the limit of the change in y over the change in x, because here we can see visually that we're getting closer and closer to the actual tangent line. And when we take that limit as it goes to 0, we're actually calculating the tangent line, which is also what we call the derivative. So we start out with our typical generalization for a tangent line, let's say as if it were a linear situation. It's an approximation, y2 minus y1, x2 minus x1. But y2 is given by x2 squared, and y1 is given by x1 squared. So we plug those into the numerator of this expression, and then we expand it out, and we cancel out the values that do cancel out here. X squared cancels out, x cancels out, We can divide through by what's left here, delta x, and we end up with delta y over delta x equals 2x plus delta x. And that's the expression that we're left with for this delta y over delta x. And we take the limit then of this expression as we go to 0. Delta x goes to 0. And when it does, the function goes to 2x. And that happens to be our derivative of this function, y equals x squared. And because we didn't, our point P could be anywhere along this line, we have a generalized expression for the slope or the tangent at any given point. So we have this approach gives us the generalization or the general derivative of this particular function, y equals x squared. And so it's interesting to note that if we did this with other functions, other polynomials, we would come up with a rule, and that rule would be, if I can write this out, maybe I have enough room. Okay, our rule would be, if we have an f of x equals a x to the n, and let's see, we got to make that an exponent. Try and, there we go. Whoops, it didn't become an exponent. Superscript. There we go. Let's take this and make it a little larger. So if we have some function f of x, generally, okay, let's just make that f of x. All right, then f prime of x, Control C, f prime of x, we'll make this a prime, will be a to the n minus x to the n minus 1. And that's a generalization. So if we start out with any function, polynomial function of any power multiplied by any constant in front of it, the derivative of that function will be a times n times x to the n minus 1. So you always reduce the power by 1, and the value of the exponent becomes a multiplier in front of x. And if we wanted to do double prime, let's say 2 derivatives, let's make this a little bigger. If we wanted to do 2 derivatives, we would have, according to this rule, we would have double prime times n minus 1. Let's make this a little bigger. and this would be -2. Okay, so you get the idea. This is a generalization that we find that when we take any polynomial function, no matter what it is, in this case we took y equals x squared, the derivative will always end up being found according to this rule. Of course, you can always take limits and find the function's derivative by taking a limit like this in every case, but it's easier to remember the rule. And in some cases, a limit is a little difficult to find, as we saw when we looked at limits. It's not always the easiest thing to find a limit. So it's just nice to know this little rule of thumb here that for polynomials this applies. We haven't looked at other functions yet, like trigonometric functions or exponential functions, but this little rule works for polynomial functions, and that forms a large segment of the functions that we deal with. So I hope this has been a little helpful to understand how we derived a derivative for a function and a generalization of the rule for polynomials that we find by applying this approach over and over again to different polynomial functions. We find that we have this generalization, and that's what's used. This rule here is basically what's used when people find the derivative for a polynomial. We don't usually go through the whole process of taking limits over and over again, because we've found that this is a generally acceptable approach that applies to every polynomial and applies according to this pattern or rule that we presented here. And normally we don't need more than one or two derivatives. Beyond that, we don't find additional derivatives are generally useful, except in certain circumstances, let's say with a Taylor series. But when you look at physical problems, mathematics used to describe physical problems, a second derivative is about as far as you go. First derivative represents velocity, and the second derivative represents acceleration. And acceleration is basically the rate of change of velocity. So anyway, I hope this has been somewhat helpful. It's a little neater graphical representation from my drawing yesterday. And I just think that what's nice about this drawing is that it shows how, as we shrink delta x, that the slope of the resulting right triangle becomes closer and closer to the actual tangent line at the point of interest, at our point of interest. Look at this line. When we have this very small triangle, this line, which I extended out, is much closer to being parallel to this tangent line than the original slope, hypotenuse slope that we started out with. So as we continue to shrink, delta x, the hypotenuse of the triangle increasingly becomes parallel to the tangent line. And in the limit, when that delta x goes to 0, it becomes exactly the tangent line at that point of interest. So that's the important concept here. So recognizing that limit and then finding the expressions that are unique to the delta y over delta x for any particular polynomial, and then applying that limit to that resulting function will give you the derivative of that function. So that's about it in a nutshell. And I'm just going to add this on as an additional supplemental video because I think the graphics are a little neater, a little easier to see. Okay, I wish you all well, and until next time.